Good morning and welcome back to Advanced Image Synthesis. Today, as promised the last time, I want to talk about REYES, which is short for Render Everything Your Eyes Ever Saw. So, no understatements here. So what is REYES? REYES is a concept. It's not a piece of software. It's an idea. It's an algorithm to, well, render everything your eyes ever saw. So to pretty much render everything. And it has been implemented into a tool called RenderMan, which is the tool of choice for a number of animated movies here. So you see a bunch of Pixar shots from a bunch of Pixar movies here, as well as a number of, well, effects used in real life action movies, such as the ones that you can see here, and number more. So what I intend to do with this lecture, as with many others, I just want to basically give you a brief overview over the basic idea, the basic content of, in this case, REYES. And if you're interested in more details, I suggest that you take a look at the literature. In particular for REYES, I would recommend that once again because it's old. It's been developed by the Lucasfilm Graphics Group, which later became ILM, in the 80s, 1980s. So that's the key point here. So why is 1980s so important? Well, it's not more important than 70s or 90s, but it's been quite a while. And been quite a while is important because it means there hasn't been so incredibly much graphics research before that. Okay, so in the 80s, graphics was sort of in its infancy, even though that's actually in the lifespan of a number of people, including me. So I was alive in the 1980s. And the advantage of looking at such a technique is that if you want to study that literature, you don't have a huge body of previous work that you also need to read to understand anything. So if you just look for the original REYES publication, you should, given that you attended, or assuming that you attended a number of my computer graphics and advanced image synthesis lecture, you should be able to kind of read this from basically beginning to end without too many issues, too many things that you don't understand, which is very different when you read a paper, a computer graphics paper today. You'll probably, as a beginner, will have to read, I don't know, 20, 30 other publications just to understand the basic ideas. So without further ado, what is this all about? Well, Lucasfilm's graphics group was kind of pioneering computer graphics for movies. Back in those days, effects in movies. So first of all, animated movies didn't exist, or computer animated movies. Of course, animated movies, Disney, well, certainly that exists, but computer animation didn't exist in movies, in shorts, or in advertisement. Not to forget advertisement. It's a big chunk of effects, and computer graphics is advertising. So, but nonetheless, computer graphics was practically non-existent. It was all based on analog technology. Animation was built on hand-drawn images, on slides that were put on top of each other, and everything was analog. And there were a bunch of pioneers, a lot of them originating from the University of Utah, and they developed a number of different computer graphics techniques. So, for instance, the Pixar imaging computer. You know Pixar from animated movies these days, but they started building hardware. They started building an imaging computer that was intended to do parts of the, well, post-processing, cutting and general post-processing of film material on a computer system. Okay, so that's what Pixar started with, and the hardware never really took off. For one reason, because there was a big push against digital technology. So people were very cautious about digital technology back in those days, which certainly has changed a lot. So their hardware wasn't very well received back then, but a lot of people got interested in the software system, and REYES was one of those things. As I said, a number of movies were developed using REYES, so I've picked a bunch of screenshots here from particularly interesting movies. I'd be happy to cover the details on those movies, Sherlock Holmes Jr. Or Wrath of Cain, and why they are so important and what's very specific about those. I'd be happy to cover those in late night coding or late night science talk, but just as a side note here, all of those images that I show here use specific computer graphics techniques for the first time, and most of those were implemented into RenderMan, which is this REYES implementation. So REYES computer scientists are sort of into abbreviations and funny abbreviations, or what they think is funny. And it's also a place in California, if I recall correctly, a point REYES, and that's a computer generated image of that part of that point REYES. Back then, that was 83. That was considered photorealistic, or at least kind of state of the art. It's obviously not photorealistic by today's standard, but that's kind of an interesting point here, and that's why I showed this image. This image created 83 by Pixar using REYES, by the way, off-point REYES. That's the fun part. That was considered extremely realistic, and so this idea of photorealism, our perception of photorealism kind of seems to shift, which is funny because I mean reality doesn't change too much, but just by being able to do more and more and more, we ought to expect more and more. Okay. So that said, what is REYES really? I mean, besides a landmark and besides this crazy abbreviation, I'd like to cite the paper, and I actually want to do this a couple of times through today's stream, which is somewhat unusual. I usually don't do this, or I didn't do this in my previous streams, to have so many quotations from a paper, but I think this paper, it doesn't build on anything, so I can actually use parts of it without having to explain too much. And I think it pretty much nails a lot of the concepts in a very nice way. So I think the wording is really nice, so that's why I like to copy an unusually large amount of text from that paper, or in general have an unusually large amount of text on the slides. So you've probably read this by now, and here's from the paper's abstract, here's a definition of REYES. It's an architecture optimized architecture, right? So it's a basic concept optimized for fast, high quality rendering of complex animated scenes. Okay, and I've highlighted here, that's not in the paper, I highlighted fast, high quality, and complex. Okay. And what I really like about this paper, that it kind of goes on and defines pretty much any term that it uses. So for instance, it defines fast. Okay, and fast is not what you think fast might be. Fast is defined in the REYES publication as being able to compute or render, we would probably say today, a feature-length film in approximately a year. I think I mentioned that before, that this is kind of the goal that industry goes for, but this doesn't really sound like super fast, right? That doesn't sound like real time. If you think about a feature-length film, feature-length basically translates to 90 to 120 minutes. So we're talking about 1.5 hours to 2 hours. Being able to render that in about a year is a significant difference from real time, right? Where in real time, the movie would be done in, well, 1.5 hours or 2 hours. So that's what fast means, okay? Why is that considered fast? Because, well, you can easily speed things up here, or you can often, not necessarily easy, but at least often speed up things in movie production by just parallelization, okay? So you have scenes that are independent from each other, that can be processed independent. Often you can process frames independent of each other. So sometimes there are animation sequences which are hard to process completely independently, because you kind of have to go through the animation, but you can nicely parallelize things. So that said, if you say, okay, well, I want to get this movie done in about a year, then, and let's just pretend things scale perfectly, than just get 365 computers and you're done in a day. So that's kind of the underlying idea, right? So that means a computer, and not necessarily it should take that amount of time in the production. And I would say folks kind of try to stick with that performance concept, but they certainly fail today. So certainly a movie, even though our computers are way more powerful, would take significantly longer to render on a single computer. And that is because, well, we go more and more into parallel systems. And so a computer, so there's more than these roughly 400 computers available for a movie. And there's one thing that is certain: if you throw more resources, more computing power, and more effect power at artists and designers, they'll use it. So that just blows up the system in complexity. So anyways, that's fast. What's high quality? That's also defined in the paper, and it says it should be virtually indistinguishable from the real thing, from real action motion picture photography. So, okay, we want photorealism in short, and we want this in a year. Now, another term that showed up in the initial definition was complex. So what does complex mean? And it's also a funny definition. It's fairly short. It says visually rich scenes. And obviously, this one is very open to interpretation. I also mentioned before that being photorealistic is apparently open to interpretation, right? And this 1 year, well, okay, I guess 1 year is undebatable, but nonetheless, with more computers, we're willing to stretch that year as well. So a lot of these things are actually pretty open. And that's, again, one of the great things about REYES, and that's the reason why it sort of survived, because the approach has changed a couple of times, but it's still true to its original goals, because the goals were very general. Again, that was 80s, that was early 80s, 1980, and just assuming that we could ever build a computer or a piece of software or an architecture, which might be hardware, software combined, to be able to generate an image, let alone a photorealistic image of visually rich scenes, seems kind of obvious today, but it certainly wasn't obvious in the 80s. Okay, so a lot of people had monochromatic monitors that could display text and would use that to display, I don't know, spreadsheets or text processing systems. Okay, so graphical user interfaces weren't the standard back then, right? Okay, so Windows for the PC mainstream market wasn't invented. Even Apple stuff was kind of in its infancy. That was pretty visionary here. So what are the requirements, or what were the requirements set up for a system to be able to achieve the goals? So the requirements that the system should be able to do, or the input that the system should be able to process, that were set in the REYES publication, where it should be able to process complex models. Well, that was kind of in the early definition, but also diverse models, and that's kind of an interesting thing. So what does it mean, diverse model? It means that we don't want to restrict ourselves to a specific type of data, such as triangle meshes, which we often do and often did also in this lecture, where I said, okay, well, you can do all of this, but we'll mainly focus on triangles. Well, it turns out REYES also does a similar trick to restrict to something, but the input should be unrestricted. So that was kind of an idea. It should support complex shading. Minimum ray tracing, even in the 80s, ray tracing was a known technique. It's actually one of the first computer graphics technique. It was developed way before rasterization, or not way, but a couple of years before rasterization. So it was well known. The system should be fast, should be speedy, have significant or sufficient image quality, and be very flexible for future editions. Let's now just look at these things in more detail. So, and as I said, the paper is nice in the sense that it defines everything that it requires. So model complexity, here's the definition of a model complexity. And it said scenes with hundreds of thousands of geometric primitives. Okay, and we're talking here about 80s. Okay, so just to get that straight, I mean, hundreds of thousands of geometric primitives seems like a bad joke today. I'm pretty sure my smartwatch can easily handle hundreds of thousands of geometric primitives. I think it has three graphics, I guess two graphics units. Anyways, so that is probably that's probably a pretty easy task for my smartwatch, certainly for any cell phone around, and it's a complete joke for any PC, let alone a powerful workstation. But again, we're talking about 80s here. Just as a kind of for those of you who haven't been around in the 80s, just to give you a rough idea, right? In the 80s, most people that were using PC system were using something that was called an 8286, or just 286 in short. 386 was just introduced. So 386 was the first 32-bit machine in that line, or the first true 32-bit machine, let's put it this way. And the 286 shipped with 640 kilobytes of memory, right? And ran at 10 megahertz. Okay, so it's no surprise that any smartwatch beat the system, because I don't really know the RAM of my smartwatch, but I'm pretty sure it's somewhere in the gigabytes. Okay, so, and this is half a megabyte, right? So requiring hundreds of thousands of geometric primitive was a gigantic thing. Okay, so I talked about model diversity a little bit already. So model diversity was basically, okay, well, we want to support pretty much anything that you throw at us, okay? And that's, of course, simple things such as triangles, quadrilaterals, so polygons, but also other objects, and in particular, so-called data amplification primitives. So those are things where you throw relatively little data as input, but that blows up significantly. A particularly nice example of that one is a fractal. Okay, so we talked about, for instance, Mandelbrot sets or I talked about this a little bit in late night coding. So if you're not familiar with fractals, they are structures that have the inherent property that they trying to frame this in simple terms here. So technically, just from the name fractal, those are things that have a fractal dimension. So meaning a dimension that is not an integer, a so-called Hausdorff dimension that's not an integer. That doesn't help you much. But what it means is those are usually objects that have a lot of detail, precisely an infinite amount of detail. They're usually self-similar, and they are built on very simple descriptions. So for instance, the Mandelbrot set that I just mentioned is built on just the function z equals z squared plus c. So it's just basically a quadratic function in a complex space, and we're interested in convergence behaviors of this function. But it's a very simple thing, and it blows up to an infinite amount of detail. So that's what an amplification primitive is. Okay, yeah, so there's some thanks for posting that. You can find tons of videos on YouTube from that area of demos. And I can suggest a few movies again towards the end today or in late night coding that we can have a look at that demonstrate some of the things that were kind of breakthrough technologies in the 80s. Things such as textures or so, all right? So things that we take for granted these days were invented then. So that's model diversity. Shading complexity is another one of those things. And that was defined pretty simple. We want programmable shaders. Again, 80s. Programmable shaders, kind of a big deal back then. And it's been a pretty big deal until pretty much the dawn of the century. So around 2000, programmable shaders made it into mainstream graphics hardware. So that is actually something that took a while before it was picked up by mainstream hardware, and then it took a couple of years for that actually become performant enough to be actually useful. So minimal ray tracing is one of those interesting things. In particular, since there's kind of this debate going on, which one's better, ray tracing or rasterization. And what I find interesting is that these folks here that developed REYES are very pragmatic, right? So they were pretty open to ideas and didn't care much about anyone thinking that method A or B were better. So they really only cared about getting stuff done, getting movies done in time. And their take on ray tracing was that it simply takes a while for ray tracing to produce an image, even though it has a bunch of advantages. But they wanted something that was faster, and they said, okay, well, we can approximate or fake, if you want to call it, a lot of the secondary effects that ray tracing is great at generating by just texture maps, by just pre-computed images. And we'll see how far we can get. And only if that fails in situations where just an approximation with a texture map, maybe an environment map or something, fails, then let's do some ray tracing to get things done. Speed, I already said, this 1 year thing, and that translates, like if you do the math, that translates down to about 3 minutes per frame. If you assume, I think that's assuming that a movie is about 90 minutes long, and if you just divide that by the number of minutes in a year, you end up with roughly 3 minutes that you have per frame. Assuming, I think that's assuming 90 minutes, 25 hertz, 25 frames per second. Today we're using usually a lot higher frame rates, 30, 60, sometimes 100 hertz. 90 hertz is also used. And there are some awkward in-betweens, like 24 point, I think 1.5 or so. So in any case, we want to dedicate an average. Average is kind of a key thing here. An average of around 3 to 5 minutes per frame, okay, to kind of stay in the budget. Image quality was also one of those points, and that's again very interesting here. What's meant with image quality, and to kind of sum things up, avoid aliasing. Right? Okay. So here's the key term. I mean, it says it starts with avoid aliasing, and then defines a little bit what aliasing is. So we don't want any type of aliasing noise. Any type of subsampling should be avoided, or artifacts from subsampling. So what that will later on distill into that we do crazy super sampling to avoid temporal artifacts, avoid moire patterns, jagged edges, because none of that is something that we observe in reality, and it's relatively easy to avoid. Not necessarily computationally easy, but well, if we just do super sampling, that's a relatively quick trick to avoid aliasing, and that's a basic criterion here. And flexibility, and that's kind of the coolest part actually for me about this approach, is that, and that's again copied literally verbatim from the paper. It's like, okay, well, we're 87, right? We're just starting here, and there will be a ton of other things be developed in the future. So let's just make sure, as much as we can, that we're open for new developments. So that's basically what flexibility says. And I think that's very that's a very cool statement to assume that we're not the greatest here. So there'll be other ideas coming in the future, and we want to make sure that those can be accommodated in the system. So those criteria led to the following design here. So I put this together in sort of a pipeline view, the design of REYES, and again, I copied a number of kind of keywords from the publication that describe the parts of the pipeline. And in the following, I again want to just go through this list and check what exactly those things are. But as a brief overview, and to finally say a little bit about what REYES actually is, it's really a rasterization system with a bunch of additions to it. So if you compare this pipeline architecture here to what we've seen before as an OpenGL pipeline or a Vulkan pipeline or a DirectX pipeline, which are really all the same thing. So basically what our graphics hardware realizes these days, you will notice that it's kind of the same. It just has different names, which is because, well, the terminology wasn't fixed back then. It's just like reading old English or German text, right? You read a number of different spellings because people haven't settled for a specific spelling yet. And here it's kind of the same thing. So if I just walk you through, check this out. So at the beginning, we got the model, okay? So in a rasterizer, we say, well, we start with geometry. We read that model, obviously. We would say we send it to our graphics board. And then there's something that's called bound and on screen. And that's kind of like the clipping that goes on in the vortex processing stage. And then there's something here about diceable and split and some loop. So we don't have loops in a normal rasterizer, but we do have a geometry shader, which kind of goes in the same direction. And we've these days got hull shader, which also kind of go in the same direction. What's called dice here, that's pretty much the rasterizer. Dicing means splitting things up into small dices, which is, well, it's pretty much what the rasterizer does. And then we have shading using textures, sampling, which is just basically a fancy word for the pixel shader stage. And then we got visibility computation, never mind the vector here, filters, and that's what we would call Z buffer and, yeah, filter to some degree blending. Okay, so in essence, that is a description of what a rasterizer looks like with a bunch of additions, and that's kind of those are kind of the key insight. Like specifically say, okay, well, there's a backdoor. Um, um, well, we'll see how that part works. So let's just walk through. Dice sound like little squares, not trying. Yes, that's correct. But what is the output of a rasterizer? Um, um, what's the output of a rasterizer? I mean, what's the shape of what's the shape of a pixel? Right? Is this a triangle? No, it's usually not not a triangle either, right? So not that these dices are one-to-one pixels. Think super sampling, right? But other than that, it's pretty much what you would expect from a rasterizer as well, to spit out little squares, right? And that's what this thing really does. Okay, let's walk through these steps a little bit. Okay, so we got the first thing, this natural coordinate idea. Okay, and what this well, let me just quickly fix something here. Okay, so we got that part fixed. So so we got this idea of natural coordinates, and the idea of natural coordinates is pretty much that each calculation in that pipeline should be carried out in the most natural coordinate system. That is a very subjective term, right? What's a natural coordinate system? And that's something that we've been using all the while. Remember, we had model coordinates to model the object. We had world coordinates in which we would place models, we would scale them, rotate them, right? Remember my car example, right? You would model a car in its own coordinate system, say 5 meter is the car's size. So I go 2.5 meter to the front wheel, 2.5 meter to the back wheel, roughly, right? So I use a natural coordinate system here. And when I place a car in the world, I will do all the computation in world coordinates, right? So my city is 10 by 10 kilometers in size, and I place the car 5 by 500 meters somewhere, right? So nonetheless, still 80s. So that was kind of a novel idea, to always use the most natural coordinate system and then simply transfer from one to the other. And as an example, which for once isn't like model and world space, if you want to do texturing, you want to do this in texture coordinates, which again is something that is very natural to us today, but it's because folks back then came up with this idea to not use one coordinate system through the entire pipeline and then kind of do some crazy mappings in your head, but do it the other way around. Take, for instance, texture coordinates and use those as a means for accessing texture information, and then bind the texture coordinates to the geometry. Okay, So another example is a visibility calculation. You want to do this in pixel coordinates, right? So if you have 2 pixels and you use a z buffer, then just compare for an x, y coordinates, its z value, and you're done. So things such as the z buffer were also invented in about that area. So a lot of things that we take for granted today originate from this. So vectorization was one of those other comments on that list. And again, that was kind of a novel idea, which is also something that I guess the entire graphics card industry built on these days. And that is that we want to be able to separate calculations. So we want calculations to be independent of each other. Like every pixel should be independent of each other. Every triangle or every primitive should be independent of each other, right? I've been preaching this at the beginning of this lecture when I talked for quite a while about rasterization hardware, that the key idea everything is built on is we want this to be as parallelizable as possible. So we're willing to sacrifice a lot of flexibility by giving up crosstalk between computations, but we gain a ton of performance from that. And that's simply referred to here as vectorization. And again, an example here, we want that things are independent of each other while still accessing similar data. So that's probably a difference between vectorization and just straightforward parallelization, is that on the one hand, we want all of this to be independent, but we want this to work on similar data so that it's at the same point cache efficient and doesn't require too much data access. Okay, and a particularly good example here is pixels that are being shaded, right? So we want every pixel to be independent, but we want to process them in some order so that all of those independent units access not the exact same, but access similar memory so that we can read a block of memory and process it and then write it out. Okay. An interesting other thing is that common representation, and that kind of, let me get myself out of the way because I got a lot of text here. And that kind of goes against the idea of flexibility at the beginning. So the paper started, the approach starts with this overarching idea that we want to be able to basically process everything. And then we suddenly say common representation, right? And the key here is that we want to support pretty much anything, but at some point we want to be able to turn it into a common representation. And what's that common representation? And the common representation is this micropolygon, okay, which are flat shaded subpixel sized quadrilaterals, okay? And that's, by the way, the output of the dicing process. So, and again, back then, folks haven't settled on words. So today, we would probably just call this subpixel, okay? So, but since that term wasn't known, I mean, it contains subpixel-sized quadrilaterals, but I guess we would simply refer this to subpixel, right? What does flat shaded mean? It means it's a thing that has a uniform color, is pretty small, it's smaller than a pixel, and its shape is a quadrilateral, okay? So not necessarily a rectangle or a square, but a quadrilateral. Okay? So we would just refer to this as subpixel today, okay? Since they lacked a name, they call this micropolygon. Okay, but you can pretty much replace this by the term subpixel. Okay, and then we want to do all of the following computations on those micropolygons. So we want to start with pretty much anything, and then turn it at some point into this micropolygon, and then work with that. And this idea is kind of similar to the idea of a ray tracer, okay? So if you just remember ray tracing or path tracing, I'd say we can also throw a ton of different things at a ray tracer, and it needs to just support pretty much one thing, an intersection computation, okay? So you can ray trace pretty much anything as long as that anything allows you to do a computation, anything to ray, where does it intersect, and give me a few parameters of that intersection. So for instance, normal and stuff. Okay, so, and it's kind of a similar idea here. We accept anything, we just want this anything to support something. And that something are two operations called bound and dice. which is, again, kind of the same idea, the ray tracer where you would want a intersect method to work. So here's another few things which are which I want to mention. So the approach should be linear. That is true for many computer graphics approaches, right? Twice as big of a scene, twice as long, but it's not true for all. So we want this to be linear, and that's today we would just say we want it to be scalable. Okay, anything that's beyond linear doesn't scale. We might be able to accept n log n, but that's about the limit of scalability. Okay, because we're generally concerned with the very large models. Okay, so for very large things, polygonal approaches such as squared or cubic, that doesn't really scale. No way that this scales to really, really large things. Then locality was another one of those requirements. I mentioned that before with vectorization. So we want all calculations to be performed locally. And that basically means not only that the computations, that similar nearby computations should access similar memory, but it also means we generally don't want global data access. Okay, and for instance, the ray tracer is a particularly good example. If I cast a primary ray, you could say it's a local computation, right? I got this one ray and then hit the surface. Well, not, because for the computation of that surface, I have to consider the entire scene, or at least the entire acceleration structure, that in essence contains the entire scene. And even if I ignore that for a second, as soon as I decide, okay, what's the color of that intersection that I found, you will have to shoot new rays, and those new rays, again, require global knowledge. And that's what we want to avoid if possible, okay? So that's one thing, and then the same is true for those procedural models, right? Fractals, similar things, these amplification primitives. We don't want to work on this large thing. And the idea of locality is, and the same is true for textures as well, is we have very little memory. We have very little memory compared to what we want to do with that. Okay, so that was certainly true when we were dealing with kilobytes of memory. Okay, but it's still true today, even though we're dealing with gigabytes of memory and sometimes terabytes of memory. So workstations tend to have a memory that's sort of in the terabytes, but believe me, complexity kind of grows along with that. So you'll never have enough memory to really store entire scenes in there, well, entirely. So entire scenes. So there's always going to be some artist that figures out, okay, well, I want more detail here. Okay? So that's what locality means. We want all computations to be bounded by some environment. Okay, and if you put all of that together, you end up with this here. So again, let me get out of the way. And I don't seriously expect you to read it, but that's pretty much REYES in pseudocode. So it fits on one slide, technically. I think if I place myself here, yeah, you can actually see everything. So it fits on one slide. And it's where some of those calls are actually will result in significant other code. But yeah, you can implement REYES in relatively little code. So that's here. That's the pseudocode. And that's also pretty much copied verbatim from the publication, and that's the whole thing in a flow graph, which you've seen before. So I think some of those parts are really trivial, right? I mean, we start with a model, we end up with a picture. I don't think I need to talk about that. And well, we somehow read the model, right? And that's an interesting thing. So a raster doesn't care, just assumes that the data is here. But if you take a more practical approach, you need to assume that there's some way to get the data, right? Which I think is interesting to include this in the rendering system. Okay, so then we got bounding, splitting, and dicing. As the first part, I said dice is sort of like rasterization. And then comes the second part. So let's just look at splitting and dicing. Notice the poor quality of that image. That's again a copy that I wanted to stick with the original images here. So that's a depiction of splitting and dicing, and that's really all I want to show about this because it nicely demonstrate the idea. So let's assume you want to render a sphere, okay? So let's assume you want to render a sphere, and you don't want to break that down into triangles or anything. You just want to say sphere, so basically radius center. If you want to render a sphere in REYES, or render really anything, you first need to support two calls, bound and dice, and split, sorry, bound, dice, and split, whereas kind of splitting and bounding go along with each other. So the idea is the following, that you first send this entire sphere and say, well, here it is, go render it. So what REYES will then do, and let me go one slide back, it'll first bound that thing, which is a fancy name for computed bounding geometry, and then do a check on the bounding geometry. Yeah, well, yeah, that is true. We'll later. I'll get to that in a second. Yeah, but you're correct. So these small things are then actually the micropolygons. So first of all, we do a bounding box computation. Okay, remember optimization. And using that bounding box computation, we can then do a quick check. Is this thing visible? If not, we'll throw it away. Okay, so that was part of my whole scene graph optimization lecture, and here we have the same idea. Okay, so we first want to figure out is something visible, and for that we do this on bounding geometries. It doesn't say do a bounding sphere, do a bounding box. It just say, well, some bounding geometry that we can check easily. Okay, so again, flexibility is kind of a key concept here. So depending on our bounding geometry, we'll have a different on-screen computation, but nonetheless, that's the basic idea. So then when we decided, okay, the thing is visible, we'll check if it's diceable. So that was the next call, is it diceable? What does that mean? It means effectively, and that's a call that we, if you think about object-oriented programming here for a second, that bound would be a call to your sphere object. Diceable would be a call that you also throw at the sphere object that returns a Boolean. Okay, so that would be, if you implement a new object in REYES, that would be a virtual method that you would have to override. Okay, so, and when is an object diceable? Well, when it's so small that we can turn it, we can rasterize it into, as we would today say, a set of subpixels, so that the number of subpixels is reasonable. Okay, and well, reasonable again depends on your hardware limits, but as I said, in a general setup, RenderMan, so ILM or Pixar's production, they do a crazy super sampling, like 1,000 by 1,000 subpixels per pixel or something. So which is way beyond the super sampling that we would normally use in real-time computer graphics. So if you say, okay, well, I don't want to create more than, I don't know, 10,000 primitives, your object would have to be significantly smaller than a pixel to be able to dice it to 1,000 times 1,000 subpixels per a pixel. Okay, so assuming that your object is still somewhat big on screen, this diceable would return no. So what happens if diceable returns no? Let me again go back to this overview. Then something called split would be called. Okay, and split would again be an operation that you would have to implement on your geometry. And that's what you see here. Okay, so here you see how the object is split into smaller objects. So what your geometry needs to support is it needs to be able to split it down into multiple smaller objects, right? Split it, for instance, in the center, left, right, or so. Okay, and in each of those objects, that generates a list of objects, right? And those are now, again, renderable primitives that support split and dice and bound and so on. So those smaller sphere segments in our example would then return their bounding box. It would be checked which one is visible and which one's not. And only the remaining pieces would again be checked if they're big enough or not. And then the process continues until we have something that is very small that we can then dice. And dice is really, as I said, it's a fancy name for rasterization. Okay, so that's kind of the overarching idea. And so if you want to throw anything at RenderMan, you would be able to subdivide using splitting, and then ultimately you would have to implement some sort of, a rasterization process. Okay, so, and then the output would be, well, a set of subpixel size flat shaded quadrilaterals or micropolygons, in other words. And then each of those micropolygons would get assigned one texture or one color. It's flat shaded. How does it get assigned one color? Well, it's got its own properties, such as color, normal, whatever. You compute lighting on that one. You have programmable shading, and you apply texture mapping to that, which again, by then was kind of a pretty big deal. Okay. The texture mapping is pretty much what we're used to, right? You got this small micro polygon, and that small micro polygon, which you can see here nicely, right? What you can see here is that our micro polygons are these quadrilaterals, but that doesn't necessarily mean that they are rectangles or squares in pixel space, right? Here you see in texture space or in object space, we got a pretty uniform dicing, right? But that can easily translate to structures that are not what we would assume a subpixel is, namely a square or at most a rectangle that is perpendicular to the viewing direction or parallel to the screen. So it doesn't necessarily have to be this way, but since it's so small, it doesn't make a really big difference. Okay. So let's finish things here. Sampling then was the next stage, and that is really just basically super sampling as we know it. So we'll take the results of that diced grid or the grid of micropolygons, and then we ultimately need to turn those back into pixels because whatever we do, the result is basically an image on screen that's made up of pixels. So we take that grid of micropolygons, and then for each pixel that it covers, we'll basically sample that grid, and we'll get a bunch of samples, and then we compute a single value, and you can refer to my lecture on anti-aliasing, how we do this. So we might use a jittered sampling pattern or a regular sampling pattern, overlapping sampling pattern, whatever. So that's pretty much super sampling. But notice there's this intermediate step, which we don't have very often in a graphics card setup, where we first generate those subpixels and then sample the subpixels again, right? Usually we have a one-to-one mapping subpixels to samples when we do rasterization. Here, those are two different things. And the idea is pretty much just simplicity, because if we allow our micropolygons, our samples, to be aligned anyway, then the dicing process becomes much simpler, right? If you think about the sphere, for instance, right? Assuming that our split part is very small, we can just output as micropolygons, we can just output sections of the sphere, right? And those are on a curved surface. And we don't have to worry about how to project those on screen. So those are just small things that make up a watertight surface, if we assume that they have a finite size, which micropolygons have. They're not points, they have a finite size, right? And then ultimately we have kind of a second rasterization step, so to say, on top of that, which we just refer to as sampling, and we read from those micropolygons. And again, this here is kind of an understatement, right? So here we probably have, well, let's say how many micropolygons end up on one patch, maybe, I don't know, I would say maybe like 3 by 3 or so. Again, those micropolygons are generally way, way smaller. But that's a parameter that you can set, right? The smaller you make them, the longer the process will take, the more bounding and splitting operations you have before you start the dice, and the more you have to do to get this done. So the next thing is culling. I kind of mentioned that before. So since we do this whole splitting thing, we do we get successively smaller and smaller objects, and those smaller and smaller objects, so we chop them off of the big one, and for each one we determine whether it's inside or outside the frustum. So we get a pretty good inside the frustum part that we only process. So there's a lot of things that are outside the frustum, and we never process them after we have done the bounding and splitting computation. Notice, however, that there will be some overlap outside the frustum, right? Even if we make this fit very perfectly, so there's this chance that what happens is that we split things up, right? So let's assume that's very small, this part here. But still, even if it's subpixel sized, a part of it might extend outside. A very, very tiny fraction might extend outside the frustum. And without too many details, if you do a projection, just that we're used to do this for in our rasterization pipeline, so you do your model view projection matrix. Remember that I said a while ago things that are outside the frustum, in particular that are in front of the near plane, which is here called hither and yon, near and far. Again, wording wasn't fixed back then. If you have objects that extend beyond the near plane, so that are closer to the near plane, crazy things happen to those coordinates. Okay, so I ask you, if you follow the exercises, to just do this. Take a coordinate that's in front of the near plane, compute a projection matrix, take a coordinate that's in front of the near plane, check what happens to it. It gets thrown behind the far plane, so crazy things happen to these points. To avoid this, we have to introduce another kind of near plane that is a little bit closer to a little bit further away from the viewer, to cull things a little earlier. Okay, so that's kind of a small detail that you have to observe. So to sum things up, because I'm going over time here, but I just want to sum this up to the last slide. How does this thing happen to render global effects such as reflections, or reflections here, environment maps that when you the entire environments reflect, or refractions, or global illumination? And the answer is pretty simple. Environment maps. And those environment maps can be computed on the fly as well. So that was kind of the first way of dealing with these things, just to get the data down. In the meantime, a lot of other approaches have been added, right? Remember, there's backdoor, there's openness. So to some degree, since the shaders are not specified what they can do and can't do, you can also run a raycaster or a path tracer in the shader, right? You can say, okay, well, now here in this programmable shader, please shoot a secondary ray, figure out global illumination for me. So that's of course very costly. It should only be used where it's necessary, but it's possible. So these stages are way more general, way more powerful than the rasterization stages that we know from a graphics API. I mean, they're kind of getting there, right? We see we see ray tracing units pop up in recent NVIDIA and AMD and also Intel APIs, right? So we're sort of getting there, but that was in there from the get-go, from the start, that if it's necessary, we can do this. And just to give you kind of a hint, ray tracing wasn't used until when it comes to animated movie, until Cars, the movie Cars, right? Animated Pixar movie Cars was the first one to use ray tracing to a certain degree, namely for the hood of the car, right? So the front hood of the car, which reflects part of the car. So in that case, environment maps didn't work out very well. So that was the first time that actually ray tracing was used, at least for a significant part, namely for all the hoods for the cars. And before that, pretty much no ray tracing was used. And with newer hardware, new approaches, better acceleration structure, and more drive to realism, more and more global illumination approaches are used in those shaders. But it's still based on the same architecture. Okay, so that's pretty much it for REYES. Again, if you're interested, just search for REYES, search publication databases for REYES. You'll find it, and it's an interesting read. Normally at that point, I would give you more time to ask questions. However, we're over time already, and so I need to keep things a little short here. So if you have any further questions, you haven't asked them now? Your fault. No, seriously, if you have any further questions, feel free to ask them on Moodle or on the Discord, on our Discord server, or in the next session, in which I intend to talk about image format, and that will also contain some insights into compression, which we will also talk about tonight in the late night coding. So I also want to talk about compression there. So there will be a significant overlap between the lecture and the late night coding. Okay, so that's it for today. And then again, I'll need to cut things short here a little bit. See you in the next session, which will be either tonight or next Tuesday. Until then, stay healthy getting your vaccination if you haven't done so, and if you can, will help staying healthy. Until then, bye-bye.